Welcome to all. In this course, Optics BSPA 303, Laser and Photosensors 5th unit, 3rd lecture. In this lecture, we will talk about relation among Einstein coefficients and condition of lasing action. In the previous lecture, we have obtained the relations while discussing interaction of radiation with matter. First, we will try to obtain the relations between them, and we will establish the conditions under what condition lasing action can take place in this slides. This is the outline that we are following in this lecture. We will begin with learning outcome, then student effective learning outcome. We will discuss Einstein coefficients, all three Einstein coefficients. Then we will obtain the relation between these coefficients, and after obtaining the relation, we will discuss the significance of their relation, especially for lasing action. We will obtain the condition of lasing action, and finally we'll end with exercise and future references. This is all that outline for this lecture. At the end of this lecture, you will learn about significance of Einstein coefficients and their application in obtaining conditions for lasing action. Einstein coefficients are the coefficients, mathematical expressions discussed and obtained for interaction of radiation with matter. In these coefficients, we have explained about spontaneous and stimulated behavior of atom. These coefficients are very helpful to obtain the more information about lasing action, whether lasing will take place or not. So we will discuss these things detailed here. The objective of this learning and the learning outcome about this that you will gain with this, you will get the ability to problem solve problem solving ability through application of theory and practical concept. The laser work was started by Einstein in a theory. In theory, he had given the idea of stimulated emission, but which was impossible to obtain stimulated emission in 1920. That concept was developed after the invention of metastable states. We know the metastable states have longer lifetime than the excited states. This concept cannot be developed with excited states because of very small lifetime, but it can be developed with longer lifetime. So this is something that I'm discussing, how you can solve problem by a combination of theories and a concept. This is the best example. Laser is the best example for this. So you will learn here how it can be. It will also help you for critical and innovative thinking and ability to collaborate this work with other disciplines. In the last lecture, we have discussed about interaction of radiation with matter. And in that interaction, we have obtained three coefficients Those coefficients are termed as Einstein coefficients. We have discussed in the last slides about three phenomena that took place whenever we strike radiation with matter. One of the phenomena is absorption or induced absorption, that is only one type, and other two phenomena about emission. One is spontaneous emission, second one is stimulated emission. For each phenomena, Einstein has given coefficients. A21 for spontaneous emission, B12 for absorption, and B21 for stimulated emission. These are the three mathematical quantities which are measure of probability of absorption or emission of light whenever light strike on any atom or molecule. And this probability is very useful for us for discussing the lasing action, whether lasing action will take place or not. Now we have obtained these three coefficients and we will try to get information from these coefficients now. How these coefficients measure probability. We will discuss these things in the coming slides. If N1 and N2 are the atoms, number of atoms in ground state and excited state, and rho r is the energy density, then the ratio of absorption per unit volume, ratio of spontaneous emission per unit volume, and ratio of stimulated emission per unit volume can be obtained. These are the equation for this. For ratio of absorption will be B12 rho r N1. Here N1 is the number of atoms in ground state and B12 is the coefficient of Einstein coefficient for absorption. Similarly, spontaneous emission A21 N2. In this case, you can see here no energy density is appeared in spontaneous emission because this is not depend on applied energy, applied radiation energy. That is why only two things are here. One is coefficient A21 and N2 is number of atoms in excited state. But in stimulated emission, what we do, we stimulate the system so that the electron move to ground state, the atom move to ground state, and that is why it also depends on applied energy. The important point here is for any reaction, for any activity, the minimum time is 10 to the minus 8 seconds. So within 10 to the minus 8 seconds or about this time, the atom wants to move in ground state. The thing is, stimulated emission is not possible before this time. So how we did this? How? And this is something where the cause of this fact is also lies. Why we couldn't find the laser in early 20th centuries? Why it took 50 years? Because of this excited state lifetime. So we have obtained B21, B12 and A21 Einstein coefficients under thermal equilibrium. And now we know this, under thermal equilibrium, the rate of absorption is equal to rate of emission. So we can, here in this equation, you can say the first one is absorption. This is your absorption. However, these two are these two are emission. So can we write this in an equation? On the left hand side only one, and on the right hand side these two. Okay, we will do it the next step. If we put one on the left hand side and then on the right hand side, then we can do this. B1 to N1 rho R on the left hand side, this is your absorption, and the emission side, two things are there: spontaneous plus stimulated. If you do this, then this is the equation at thermal equilibrium. Now, as you see, these two quantities having rho R, can we bring this here? If we bring this on this side and this on the other side, then this will be the answer. Rho R B1 to N1, B21 N2, A21 N2. Rho R I am taking common here, and if you just find out the value of rho R, you will be here A21 up into N2 upon this. Just see this. Here we just bring this in the denominator of A21 N2. So even you can take B12 and B21 from there, like this. You can write like this, and this is your value of density. In our equation, we have N1 by N2. To get the value of N1 by N2, we know from Boltzmann distribution, then if N1 is the number of atom at any state, then N1 can be written as N1 is equal to N0 e to the power minus E1 over kT, where N0 is the total number of atoms at that state and N1 is the state at any time t. So obviously N1 is less than N0. Now this T is the temperature, absolute temperature, and K is the Boltzmann constant. E1 is the energy of that level. Similarly, you can also calculate N2. N2 can also be written as N0 e to the power minus E2 over kT. If we have these two, we can also obtain N1 by N2 to check. If we do the N1 by N2, then you can say here this is minus E1 and this is minus E2, which when you here you are keeping N2 in the denominator, so when it go in the upward direction in the numerator, it will be positive. So finally E2 minus E1 over kT. Now we have the equation in the past, you might know about rho R. If you there we are having the value of this N1 by N2. If you put that value in that equation, the equation will be modified as rho R is equal to A21 over B21 in the bracket 1 upon B12 over B21 e to the power minus K1 minus K2 upon TAT 1 minus 1. So this is your energy. So we have obtained expression for energy density, and we know this here B12 and B21 are there. This B12 and B21 both are for stimulated absorption and emission probabilities. We always consider these two probabilities are same. The probability of stimulated absorption is always equal to stimulated emission, and that is why we can put this as equal and 1. If we use this as 1 and the difference between the two level is as h nu, then the equation may be reduced to like this: rho r is equal to A21 over B21 1 upon e to the power minus e to the power 1 upon e to the power h nu over k2 minus 1. We know from the radiation formula that rho r can be written as 8 pi h nu q over mu q upon c cube 1 upon e to the power h nu over kt minus 1. If you compare these two equations, this is your first equation that calculated by you, and this equation you obtained for radiation formula. Then if you compare this, then you will find these two must be equal. These two equations are same. For consistency, you can say this will be the equation. A21 over B21 should be equal to 8 pi h nu cube mu cube upon c cube. Now mind this A21 is your coefficient for spontaneous emission, whether B21 is stimulated emission. This sometimes this formula may be asked in the exams also. We have taken these two equations from whatever we have discussed in the previous slides. These are the two takeaway notes. B12 is equal to B21. This means the probability of spontaneous emission is same as that of induced absorption. If two processes will occur in equal rates, so there is no population inversion can be attained in two systems. And these two are also always having same probability. In the second, we have got the relation between A21 and B21. The ratio of spontaneous emission and stimulated emission is proportional to nu cube. Frequency, it depends on cube of the frequency. The probability of spontaneous emission dominates over induced emission, and as more as the energy difference between the two states increases. So these are the two things that we can derive from there, we can obtain from there. There is always a competition between these three mechanisms: absorption, stimulated emission, and spontaneous emission. Basically, these three mechanisms always present at any time. But to make a laser medium, condition has to be found that favor stimulated emission over absorption and spontaneous emission. We will see these things later in the formulas also. Stimulated emission is more important for lasing action. However, spontaneous is very common. Almost all the places spontaneous emission occurs. But we need stimulated emission for lasing action. Not only need, but to a great extent. Now for this, we have to think about right medium and right conditions for lasing action, for get good lasing action. So after development of this, we will also think about how these conditions can be developed. First thing is what is needed for this. Then we will think about how the condition can be developed for better results. As we know, the spontaneous emission is the fastest emission and naturally tends to empty the upper level whenever spontaneous emission takes place. So this level has to be emptied faster by stimulate emission. It has been proved that the stimulate emission is much more likely to happen if the medium is flooded with light. So we have to flood light all the time. We have to confine the system in a cavity so that more light should be there. These are the things that I'm talking about to think over these issues. If we just try to obtain two ratios, the ratio between stimulated emission and stimulated emission and ratio of absorption, then we can obtain something. In the case of stimulated emission, energy is there and so the energy will be in absorption also, so both will be cancelled out. And in the case of stimulated emission, which depends on N2 and absorption is depend on N1, so you will be left with N2 over N1. The value of this ratio must be greater than 1 for ledging action, and that is why we have written here that the number of atoms in the excited state must be greater than lower state. This phenomena, this is called population inversion. Normally this doesn't happen. We will discuss these things in detail. We want more atom in excited state than ground for this. The process by which we do this, which is called pumping, we will discuss in detail in next lecture. But we must know that N2 must be greater than N1 for ledging action. This is the first requirement for ledging action. We have also discussed the ratio A21 over B21 in the previous slide. And A21 represents spontaneous emission and B21 stimulated. So the ratio should be less than 1 so that more stimulated emission to take place than spontaneous. This is the condition and the condition of ledging action. Whenever we obtain the ratio of stimulated emission probability to spontaneous emission probability, then we will reach to this conclusion that the rho also must be very high. Must have high energy density. You must use high energy density for this. So your rho, as we have discussed in the previous slides, this rho must be greater than 1. Here I have represented this rho by E. You can change it to rho. These are rho. So that is very important for us. Two exercise questions I am giving you to think. All the questions are conceptual. Why we consider B12 and B21 both coefficients equal? What is the advantage of this? And what if we will not consider these equal? question is, can you comment on the fact why it took about 40 years to develop laser after Einstein theory? Einstein has given this theory in 1922. Then after that 40 years we took to develop. Think over this and write down these answers. These are the books for reference you can use. You can use Engineering Physics by Avadnuru and Shirsagar as an publication. This link we have given especially for electronic spectra for various light sources. Lasing action and the use of Einstein coefficient can be also be obtained by various lectures on the website. Thank you all. We have developed the condition for lasing action. Now, in the next lecture, we will talk about how these conditions can be achieved and what are some important terms in laser. Thank you.